Hello students, this presentation is intended to summarize the polyatomic species molecular orbital theory which is included in your syllabus paper 2 unit 1. Well, already we have discussed in our regular teaching learning session about the polyatomic species in detail. But I thought that it would be easier for you if I summarize the entire presentation for the sake of understanding. Polyatomic species we had discussed with respect to LCAO method, that is linear combination of atomic orbital method. As we have seen, this method is purely based on wave mechanics, and as per the wave mechanics, symmetry adapted linear combination, that is SALC, is the basis to explain molecular orbital formation in polyatomic species. Now here, as per the syllabus, the molecules included in our regular curriculum, that is beryllium hydride, water, trihydrogen molecule and molecular ion, that is trihydrogen molecular ion. So these are the species which we are going to deal in this summary. Differences between valence bond theory and molecular orbital theory that we have to first discuss. So valence bond theory, which we have been discussing since long, it is based on the hybridization of central metal orbitals, whereas molecular orbital theory is purely based on overlapping of ligand orbitals. That means it is not giving much importance to the central metal orbitals, but it considers that overall overlapping of ligand orbitals with metal orbitals gives rise to molecular orbital. One more important point which is to be discussed under these differences, that is valence bond theory does not take into account the symmetry of orbitals when the electrons are accepted, whereas molecular orbital theory is purely symmetry based. So overlapping of ligand orbitals with molecular orbital is purely symmetry. Now look at the steps in formation of polyatomic molecular orbital. Now these are for the sake of understanding. If we follow the steps, based on these steps, the entire construction of molecular orbital diagram is based. So one has to follow these steps before construction of molecular orbital diagram. The first step says that one has to identify the central atom in the molecule, and one has to also identify which are the peripheral atoms. Those peripheral atoms can be called as ligand atoms. Then step 2, consider valence electron configuration of central atom, that is outer electron configuration of central atom. Step 3, we have to locate which are the outer orbitals available from ligand. They can mix with each other and form group orbitals. So step 3 is formation of group orbitals by the ligand. Step 4 is, once the ligand orbitals are formed, they will overlap with matching symmetry central metal atom orbitals to form molecular orbitals. Step 5, that is once the molecular orbital are formed, one has to label the molecular orbitals. Depending upon the symmetry, one has to label them as sigma and pi molecular orbital. One thing to be registered in mind, that is total number of molecular orbitals is always equal to the total number of atomic orbitals of all the atoms combining together. Next, that is all these steps together we have to consider for first polyatomic species, that is beryllium dihydride. Beryllium dihydride is a triatomic molecule. It has central atom beryllium and peripheral atoms are 2 hydrogen atoms. After identification of central atom and ligand, one has to see what are the group orbitals formed. There are two 1s orbitals available from two hydrogens which make available two group orbitals. One is formed by addition, one formed by subtraction. Next step, that is these group orbitals, they are overlapping with matching symmetry beryllium atomic orbitals to form the corresponding molecular orbital. So here we see the combination pattern. In this combination, which is called as symmetry adapted linear combination. Here side 2s, which is a wave function of 2s orbital from central atom beryllium, combines with group orbital psi 1 and it will give us two molecular orbital. One will be molecular orbital, that is bonding molecular orbital, another will be anti-bonding molecular orbital. As they are originated from s orbital, they will have the symmetry, that is sigma. So sigma s and sigma star s are the two molecular orbitals formed by the first combination. Second combination, that is the available group orbital is psi 2 from hydrogen. So this psi 2, it is looking forward to overlap with psi 2pz, which is a atomic orbital from beryllium. And therefore second combination leads to formation of again a set of two molecular orbital. One will be bonding, one will be anti-bonding, and we will label them as sigma pz and sigma star pz because they are originated from pz atomic orbital. Total number of molecular orbitals therefore formed are 4, out of which 2 are bonding and 2 are anti. On this basis, one has to construct the molecular orbital energy level diagram. Here it is the general diagram showing energy arrow, and all the orbitals, they are arranged according to increasing energy order. Beryllium, its all energy levels are placed at higher level, whereas hydrogen, we can see that its energy levels are at lower level. This is due to the electronegative difference. Hydrogen atom with respect to beryllium is more electronegative, therefore its orbitals are placed at lower energy level. Then after arranging the atomic orbitals of beryllium and hydrogen, central portion is nothing but the molecular orbitals formed by combination of beryllium and hydrogen. In detail, we can exhibit here through this slide, which shows that 2s and 2p set of orbitals of beryllium, and here on the right hand side we are denoting the group orbitals of two hydrogen atoms. According to our combination pattern, psi 1 is combining with 2s, and therefore we are showing the combination through these plain drawn lines, and we can show the formation of two molecular orbital sigma s and sigma star s. Similarly, second group orbital psi 2. Psi 2 is combining with available matching symmetry 2pz to form sigma 2pz, that is bonding, and sigma star 2pz anti-bonding molecular orbital. Remaining two orbitals of beryllium 2px and 2py, since they do not have any group orbital available, therefore remain as non-bonding. So we will count the total number of molecular orbital and how many are occupied. Filling of electron takes place owing to Abou's principle. So here total number of electrons are 2 from beryllium and 2 from hydrogen. Total 4 electrons are occupied, that is 2 in sigma s lowest energy level, next 2 electrons occupied in the next energy level. So both the bonding molecular orbitals are filled with 4 electrons. So two bonding pairs we observe, they correspond to two covalent bonds with central beryllium, and therefore beryllium at the center linked to two hydrogen atoms forming a linear geometry, and the two bonding pairs are delocalized over three atoms in beryllium dihydride molecule. Now coming to the next polyatomic species that is included in our syllabus, that is water. Again here we will identify the central atom as oxygen and peripheral atom as two hydrogens. One can jump to the conclusion that since it is resembling with beryllium dihydride, both will have the same geometry, that is linear. But it is not so. It is proved that water does not have the linear geometry, but it is angular. The reason being two lone pair of electrons present on oxygen, due to lone pair bond pair repulsion, the two peripheral hydrogen atoms shift from their original position and making the geometry as angular. Now this geometry is going to affect the molecular orbital formation because the spatial arrangement of orbital changes. Here, in case of oxygen, the 2px orbital comes closer to 1s orbitals of two hydrogen atoms. Now, due to this mixing of 1s orbitals of hydrogen atoms and 2px orbital of oxygen can take place. This leads to unusual type of overlapping which is shown by water molecule, and it affects even the molecular orbital energy level diagram. So one has to remember two things here, that angular geometry of central atom oxygen which is forming with two hydrogen atoms, the geometry is angular and it is going to affect the molecular orbital formation. Stepwise formation of molecular orbitals in water molecule, if we consider, then first point is formation of group orbitals. As we are aware that two hydrogen atoms will form two group orbital, one by addition, one by subtraction. We will label them as psi1 and psi2. They are going to overlap with matching symmetry orbitals of oxygen. Here one has to note that in case of oxygen, there are available matching symmetry orbital 2x, 2pz, but at the same time 2px orbital, which otherwise remains as non-bonding, is having its lobes close to the group orbitals. Therefore, it is also taking part in the combination. So one group orbital ideally combines with one atomic orbital, but in case of oxygen, due to angular geometry, 2px orbital which mixes with 2s orbital and then overlaps with group orbital, becomes slightly unusual symmetry adapted linear combination pattern for water molecule. Look at the first combination, three atomic orbitals are combining, that is group orbital psi1 combining simultaneously with 2s and 2px. We are having its wave function as psi. So there is combination of three atomic orbitals leading to formation of three molecular orbitals, out of which two will be bonding and one will be anti-bonding. That is, pure bonding is sigma 2s. Sigma 2px is partially bonding because 2px is not originally having matching symmetry, but due to angular geometry it acquires some s character because it is combining with 2s, and therefore 2px has some s character and it leads to bonding and anti-bonding molecular orbital. Therefore, there is formation of three molecular orbitals with this combination. Look at the second Salk combination, that is psi2 group orbital. It combines with psi2pz, which is a regular combination. two atomic orbitals are here combining, leading to formation of two molecular orbitals. One is bonding and one is anti-bonding, labeled as sigma 2pz and sigma star 2pz. Okay, so with this combination pattern, we are getting 5 molecular orbital, out of which 3 anti-bonding. The same combination is represented for the sake of understanding in a very lucid way and showing formation of 5 molecular orbitals, out of which 3 bonding and sigma 2s, and therefore sigma 2s in angular geometry, which is shown as occupying the lower energy level as compared to that of the linear geometry. The reason is the peripheral hydrogen atoms are more close in angular geometry. Next, we are showing the slightly elevated 2pz for angular geometry, whereas for linear geometry sigma 2pz is comparatively lower level. The reason is, in case of linear geometry, 2pz orbitals, they undergo overlapping through internuclear axis, therefore overlapping is strong and energy level is low. In angular geometry, there is no overlapping of 2pz orbitals through internuclear axis, so slightly its energy level is high. Next, that is we are showing that is 2px arrangement. In linear geometry, 2px remains as non-bonding and therefore its energy level is parallel to that of the atomic orbitals. But in case of angular geometry, 2px orbital coming close to the group orbitals, that is, it is very close to the peripheral hydrogen atoms. Therefore, overlapping is strong and hence the energy level is low. The remaining last orbital, 2py orbital, it remains as non-bonding in angular geometry as well as it remains as non-bonding even in linear geometry. So in both the cases, 2py, they are having the similar line of energy level. This is the Walsh correlation diagram, helps to understand the comparative energy level, and accordingly it proves that angular geometry is more stable compared to linear geometry. The last polyatomic species which is included in our syllabus is trihydrogen molecule, which is a hypothetical molecule because it is very unstable and its existence is not proved. Central atom is hydrogen and peripheral atoms are also same. So we will consider that central atom hydrogen Hc and the two peripheral hydrogen as Ha and Hb having linear geometry. Peripheral hydrogen atoms, as usual, they will form two group orbital, one by addition, one by subtraction, and labeled as Psi1 and Psi2. Psi1, which is a group orbital, then combines with the central atom Psi s, that is only orbital, one s orbital available with the central atom. This combination will lead to formation of two molecular orbital, one will be bonding, one will be anti-bonding, bonding labeled as sigma s, anti-bonding as sigma star s. Next is that is Psi2 group orbital, but it does not have any matching symmetry orbital with the central 1s orbital. Already it is consumed in the first combination. So Psi2 group orbital, we can say that it remains as non-bonding. So total 3 molecular orbitals are formed, one bonding, one anti-bonding. We have to see 3 sigma formation, that is anti-bonding molecular. In linear geometry, we can say that perfectly anti-bonding situation here. Central atom has negative wave sign and two peripheral atoms are having positive wave sign. So it is purely anti-bonding. In case of triangular geometry, there is a negative wave function carried by the central atom, but The two peripheral atoms which are carrying the same wave function, they are close to each other owing to the definition of bonding molecular orbital. When the similar wave function are close to each other, they will undergo addition. If addition is undergoing, that leads to bonding situation. That means 3 sigma energy level will be slightly lowered. It will be towards bonding molecular orbital. So compared to 3 sigma energy level in linear geometry, in triangular geometry 3 sigma level will be slightly lowered. If we consider these differences in triangular H3 geometry, then this is the molecular orbital diagram we obtained for molecular ion H3 plus. Here one electron is lost from 1s orbital of central atom. Two group orbitals are intact as it is. So total number of electrons are 2. They are occupied at lower energy level. 1 sigma remains as it is. What we see is the difference, that is 2 sigma which was earlier non-bonding in trihydrogen atomic molecule. Now that 2 sigma is elevated and slightly gone up, whereas 3 sigma which was anti-bonding in trihydrogen plain molecule, it has slightly coming down, it has lowered its energy, almost it is comparable to that of 2 sigma. So a situation is such that 2 sigma and 3 sigma occupy the same energy level and therefore they are labeled as E. E stands for doubly degenerate orbital. Doubly degenerate, that is when two orbitals occupying same energy level, it is said as E, and we are labeling 1 sigma as A. A stands for, that is singly, that is it is the only single orbital present at this energy level. Okay, so we are labeling as A and E, that is for the single orbital and two orbitals on the top energy level. So this type of situation is stable because here now almost all the energy levels are comparable. 1 sigma, that is bonding, 2 sigma and 3 sigma at the same energy level. And finally, Wolf's diagram for trihydrogen molecule. Left hand side linear geometry, right hand side angular geometry. We have total 3 molecular orbital, 1 sigma, 2 sigma and 3 sigma. Let us start with 1 sigma. In linear geometry, 1 sigma slightly at higher energy level. In triangular geometry, slightly at lower level. Reason already we have discussed. The reason is two peripheral hydrogen are close to each other, so overlapping is strong in trigonal geometry. Next is level, that is 2 sigma. 2 sigma remains as non-bonding in linear geometry, but slightly its level we can see that 2 sigma gone to higher level in case of angular geometry because of the positive and negative wave function. They are close to each other and therefore they are attracted and excited. So slightly 2 sigma goes to higher level. 3 sigma level. 3 sigma remains as anti-bonding in linear geometry, but its energy level is reduced when it is angular geometry. Why it is reduced? Because the angular geometry peripheral hydrogen atoms, that is their wave functions, they are positive wave functions very close to each other, which is an addition. When same wave functions are close to each other, undergo addition. Now this type of situation leads to lowering of energy. So 3 sigma, which was having anti-bonding in linear geometry, slightly its energy level is reduced, almost parallel to 2 sigma. So in bonding and anti-bonding molecular orbital energy level diagram for triangular trihydrogen molecular ion, we are showing 1 sigma and this is 2 sigma and 3 sigma at same energy level.